Hello, everyone. Welcome again to PyData Global 2024. We are very excited to have all of you join from around the world today. I'm Conrad, one of the co-chairs for the conferences. Pleasure to introduce Dr. Hannes Mühleisen. He is the creator of DuckDB, and he will be talking to us about changing data with confidence using DuckDB. Thank you. Please take it away.
Thank you. Just give me a second to share my screen here. And then I have to click this button. Can you see the big DuckDB logo?
Yep.
Very good. All right. Yes, hello, everyone. My name is Hannes Mühleisen. Thanks for the introduction. And I'm indeed one of the people behind DuckDB. Here today to talk about changing data with confidence using DuckDB. And confidence is an important word for us here at the Team DuckDB. It's because we have sort of noticed that many people have a sort of problematic relationship with their data. Data is generally feared. Like anything that stops fitting in Excel, people are terrified. It's my experience, after working with data people for a while. And so we kind of set out to change that because we like tables, and we feel like that there should actually be no need to be terrified of data, right? Like this has, in my opinion, this fear has to do a lot with tools being difficult to use, with general knowledge gaps perhaps. But yeah, we set out to change that, as our mission is to get people to get to data confidence. And the vehicle that we have created to increase people's confidence in their abilities to wrangle data is DuckDB. So in case you don't know, DuckDB is a free and open source data management system. It's special because it's analytical focused. It's in-process architecture. And yeah, it's pretty interesting to work on a database system. In case you have ever tried that, I can not entirely recommend the experience. There were a lot of SQL things I had to learn. But speaking of SQL, DuckDB is a relational system, which means it does speak SQL, among other things. We also have some programmatic access methods. But the fundamental abstraction are tables. We can store things like nested types and so on if you want to have more rich data types. But fundamentally, it's a SQL system. And I've already mentioned it that DuckDB is trying to be simple. We have 0 external dependencies. It's one big sort of collection of C++. It's ultra portable. It has no external dependencies. It doesn't make use of any sort of special instructions or things like that. It is a fairly small binary, and it does not require any container, Docker, root, anything server setup or anything of the like. You just download the binary, or indeed you can just pip install it. Here is the screenshot of installing DuckDB on an empty pip. You can see, you just say pip install DuckDB, you download 15 megabytes of stuff, and there you are, you have DuckDB. And after that, you can, for example, run DuckDB from Python. There's also other ways of talking to it, like a CLI or R API or Java API or God knows which API. But basically, you can then import DuckDB here in this example in your Python shell and run SQL queries. Pretty simple. It runs anywhere, Mac, Linux, Windows. As I said, it's meant to be ultra portable. And I think what's also interesting about DuckDB is that it's really batteries included, much like Python. Which, by the way, in case you didn't know, Python was also created here in Amsterdam. And it's actually only, I would say, 100 meters away from where I'm standing right now, where Guido's office was when he created Python, just as a side note. But DuckDB is also batteries included, learn from the best. So we have, for data, we have transactions, we have full asset compliance, we have multi-version concurrency control, more about that later. We have persistence, extensive support for relational transformations like joins, aggregates, window functions, you name it. DuckDB can out of the box read Parquet files, write Parquet files. We have, I think, the world's best CSV reader. We can read JSON files. As of today, we can read Avro files. And you can connect to a zoo of other things like cloud storage, S3. You can talk directly to Postgres. You can talk directly to MySQL. You can talk directly to SQLite. You can import and export data with Arrow. You have, as I mentioned already, you have clients for R, Python, Java, and I don't know, 20 other languages, it's getting a bit hard to follow at this point. So even though we are really trying to sort of copy some of the simplicity of maybe something like SQLite, we really try to, still not sort of, rob you of features that people kind of expect from data management systems. DuckDB is also fast. DuckDB has a state-of-the-art query execution engine. It is technology that was kind of known to researchers for a while, but so far has been hidden in a very few commercial products. It's a vectorized execution engine. It's one of the sort of two paradigms of writing analytical execution engines right now. People always ask me, what exactly makes DuckDB fast? And I always say it's magic. Of course, we know that any sufficiently advanced technology is indistinguishable from magic. And it's actually the culmination of decades of research, also here in Amsterdam, in analytical database systems. Many people got their PhD working on this stuff. But for you as a user, what is often the most visible effect of DuckDB being fast and efficient is that your computer gets warm. So DuckDB can automatically parallelize queries across all the available CPU cores. But again, blind parallelization is not enough. Things like Spark also parallelize, but then they suffer from a kind of low per core efficiency. DuckDB, on the contrast, has highly efficient C++ implementation for the operators. And as a result, we have very high per core efficiency. DuckDB can use the disk if there's not enough memory to complete a query. And again, all of this happens completely automatically. And DuckDB is free. It's free and MIT licensed. We are actually not VC funded, so DuckDB is not a project that is in threat of a rug pull in the near future. We have a non-profit that's holding all the IP in DuckDB. And then there's a commercial company called DuckDB Labs that I'm heading that sells consulting and support services for DuckDB. And with this revenue, we basically fund the entire show. So we have a viable and long-term funding model to basically keep DuckDB free for the time coming. And DuckDB loves Python. So Python is actually one of our primary APIs. A lot of cutting-edge DuckDB features come to the Python API first. I mean, first they come to C++, and then usually afterwards they come to the Python API. So, oops, that was not great. Something happened. Not sure what happened here. I'll just go back. So DuckDB has some unique features in Python land. So one of the interesting things is that DuckDB can read pandas data frames directly, because the architecture of DuckDB is different from what you maybe know from database systems, is where we actually run within whatever process the user is interacting with. So for example, in the case of Python, we just run directly in the Python process. And that means you can directly access things that are living inside that Python process, like data frames. So DuckDB understands the in-memory binary layout of data frames. And we can also directly turn the results of any queries back into pandas data frames within the same process. That's quite efficient. As far as I know, we are the only really database management system that can do this. The same trick also works with arrows. So if your tools can read and write arrow structures, then you can directly pass those structures to a DuckDB instance, and you can read them as if they were tables that are in DuckDB already. And you can again take the results that come out of DuckDB and put them back into arrow structures with minimal overhead. And that really enables a bunch of really interesting use cases that maybe with traditional systems like Postgres would not be possible because of the immense overhead of transferring data over a socket. Okay, so now let's talk about change. So change. Change is as old as the universe. There's wonderful quotes from Greek philosophers on this. But somehow the Python data stack treats changes as a complete afterthought. So if you think about it, like a data frame is something that's completely static. There is really no notion of changing this data frame without just completely recreating it. There is like no notion of updates really. And there's also no notion of sort of transactionality. But change is something that is inevitable, and data changes. And we have to basically be able to do better than to completely reload from scratch. So I've collected some examples from sort of Python data interactions. So here we have a a pretty simple data frame here in the upper example, where we just have a data frame with one column A, 1, 2, 3. And now we have this sort of pattern where we assign df to an operation on the df. And in this case, we make a small mistake. We filter A bigger than 4. Obviously, there is no 4, so now df is empty. And there is no undo here, right? So the only thing that you can do now is go back to wherever you got the data frame from. And that's fine if that's a tiny file, but that's problematic when when you just spend 5 hours creating this data frame. Below is another example. Imagine we are trying to write a data frame to a file in Python land. For example, you can write it to a pickle or Parquet, or I don't know. But imagine now your Python process crashes, and now we're trying to read this thing again from disk, and it will just yell at us that there is some sort of problem with unpickling this because we ended up writing a partial file to disk. That's not great. Here's another example. There's lots of funny race conditions in the Python data stack. So imagine you have two sort of threads here. One is powering a dashboard, for example, and it's reading its input data from a CSV file here. So it's reading the CSV file and then does something with the df to power the dashboard. And then we have another thread maybe that is a background refresh thread that does something to prepare the df and then writes it to a CSV. You can probably imagine there's lots of funny race conditions here. So we can read an old file, we can read an empty file, we can read a partial file, we can fail because the file is in some really inconsistent state. The write might even fail because of Windows treating logs kind of funny. Fun times. We also have this issue that whenever we have a data science project, that we end up with these endless folders that are this wild collection of variations of the same data, subsets, transformations, scripts, all that stuff. And so I want to today show you a little bit about analytics on ACID. So there is actually, for those who don't know, ACID is this fundamental sort of guarantee that relational, traditional database management systems give to users. And these are, I want to say, rules written in blood, much like the rules that govern aviation. The ACID principles are something that have emerged from decades of data management practice as a good idea, and something that you kind of want your data system or your data environment to provide, because the alternative is that you as a sort of app developer or data analyst have to sort of deal with the fallout of all these, of not guaranteeing these ACID properties, and you really don't want to do that. So I'm going to go a bit over these 4 properties and tell you how this might be useful in analytical use cases. So first, we have atomicity. It sounds really cool, atomic. I mean, it used to be cool in the 50s. Atomicity, the idea is that any change to data either happens completely or not at all. This is pretty unheard of, and this can be many different changes to many different sort of data sets. That can be schema changes, can be all sorts of things. This is unheard of in Python. While there is some protection that you don't accidentally delete a data frame if something happens in your transformation, there's sort of no notion of bundling changes to multiple data frames. But in databases, there is. So here's an example. We create a table, and these boxes here are essentially the transactional boundary. So every green box here is a single transaction. So we create a table customer. Okay, that's pretty simple. And now we actually use transactional. So the syntax is here, begin transaction, and commit to bind these 2 inserts together. So we insert 2 rows, DuckDB and polars. And indeed, if we then run the query, which is also happening in a transaction, it will basically see this state because the transaction that inserted them has committed before, and we'll see exactly those 2 values. But this is really, so this is the happy path. Everything goes well. Again, it's cool to bind sort of things together so they either happen together or not at all. You should also note that usually database management systems, when you don't say begin transaction, it will operate in something called auto commit mode, where it's implied. So if you have a single statement, we have an implied begin commit transaction and commit before and after. Here is an example where we have now, in this table that we have just created, we trying to insert another value. So in this table customer, we're inserting another value called ClickHouse, and then for some reason we decide that's not what we want. So we can roll back. We can actually not make this change happen, and if we run the query again, then you will see that the value has not been inserted, right? So this is a user sort of triggered rollback. I will show an example of a automatic rollback in a bit. This, of course, is really interesting also in things like analytics. So the previous examples were kind of from the textbook of databases. Here's an example that's a bit more interesting. So here we're creating a table. In DuckDB, you can create a table basically directly from a CSV file, like so. You say create table people as select star. The select star is actually optional. As select star from people.csv. And now we run another transaction because we now maybe want to modify this data bit. So we start a transaction. We say, for example, we update the table to remove all the values where the age is nonsensical minus 99, because that actually means now. And now we run this delete where the name is not equal to a non-existing name, and oops, we just deleted all the rows in this table. However, it's not a problem. We end a transaction. We can just roll back and nothing has happened. The previous change hasn't happened. This change hasn't happened. And we are just back having our table as if it existed directly after the load. This can be glued together to do some interesting things. Like, for example, here we have a bit more complex transaction that creates a table. So in DuckDB, table creation is also transactional. So we create a table in this transaction. We copy, again, a bunch of entries in this table from a CSV file. We do this update again that sets some values to null. That makes no sense. And then we have this interesting sort of hack here where we can actually have a case statement that will trigger an error whenever the count, sort of the number of rows in this table, isn't 1 million, which, let's assume that's the amount of rows we expect from the CSV file. So that's really cool, because that means that whenever this check fails, an error is triggered, and the commit, which is after it, will actually not go through it. The transaction will be automatically rolled back. I will show more examples about that in a second. The second one in asset is the consistency. So the consistency basically means that we can have constraints of our database that basically restrict the kind of data we can have in them. And that's something that's frowned upon for some reason in analytics, because it tends to make things slower. But DuckDB actually has a state-of-the-art index implementation. It's funnily also called the art index. And that actually is optimized for analytical use cases, and that can make checks on these consistency conditions quite efficient. So here I'll have an example. We'll create another table. This time we have a primary key. For those of you who know databases, this is pretty obvious, but the primary key basically says the ID column can only have unique values. Okay, so we insert into the customer. We have a values DuckDB library. So we try to insert another value, this time with the same primary key, the same 42, and that will be automatically rolled back. And this also is very useful in analytics. So for example, we create the same table, and now we copy a bunch of customers from a CSV file into that table. And let's say for some reason, we accidentally try to load the same table twice. It has certainly happened to me. I press like up and enter again, and then everything was kind of screwed up. But in this case, this cannot happen because, again, the constraint error will prevent this transaction from completing. It's very nice. The next I is isolation. So I had this example before where we have this dashboard that's trying to show some data to a user, and then have another thread that is running the refresh. So DuckDB has this multi-version concurrency control that's specifically designed to make analytics go fast, and I'll show a little benchmark later. It basically means that these two things can happen completely isolated from each other at the same time in parallel, and it uses a scheme called optimistic concurrency control to not sort of slow down either of them. And if there's no conflicting changes being made, both transactions can complete. And also ensures that each transaction sees a consistent state of the database. It means that you don't see partial changes from another transaction. You don't see tables that are created in another transaction but haven't been committed yet. These kind of cool things, right? And you also never see any changes that have been rolled back. It's a really cool feature. And finally, on the D, we have durability. People don't really think about durability all that much because hardware has gotten super reliable. Most of the time, data frame people store data as CSV files anyway, and just eat the performance hit to load from scratch every time the script runs. So if you do that and your hard disk doesn't break, then I suppose the data is somewhat durable. But I've shown an example earlier with the pickles where this goes wrong. Here's another example where this goes wrong. Here I have a short Python script. So I was creating a DuckDB instance, again, that runs in your process, really cool, so you don't need a server or anything. But now I'm running 2 transactions. I'm creating a table, excuse me. I'm creating a table. I'm inserting some values into it. And now and these are auto commits, so these are not committed. And then I'm beginning a transaction with the .begin. And now I'm inserting another row into the table. But then something bad happens. I'm just simulating in here with the os.kill. But basically, my computer crashes or my process goes down or something like that. And there's in DuckDB 3 things are not guaranteed. First, the table exists. Second, the first value, DuckDB labs, has been written to disk and actually f-synced, so the caches have been flushed. And the third thing that's guaranteed is that the second value, real by the duck, is not part of the table whenever you restart reading the database, and never will be. That's a really cool feature. And I'll show you an example why this is cool, or why it's important. It's just an example that I ran in myself. Here is a picture of a hardware device I have at home, and it's kept bricking itself. And I found lots of people that had the same problem happen to them. After some investigation, I found that that's due to MongoDB not actually persisting changes durable to disk, and whenever the power failed, it would sort of brick the internal databases. So it's not what you want. You want a database or a system that is ACID, so you can be safe. Finally, I want to talk about performance. So performance is something that's, in my opinion, a bit overrated in terms of data analysis. We have a lot of people, screaming on the internet that X is faster than Y, and we at Team DuckDB generally don't want to do that, because while it's nice to be fast at benchmarks, and sometimes we're fast at benchmarks, people tend to underestimate the end-to-end sort of cost in running things, right? You have a user sitting in front of this computer, and if they are blocked for 5 minutes because your syntax is weird, that's going to be much worse than if your CSV read is 10% slower, right? But regardless, people also think that having transactional guarantees actually slows things down unbearably. So, in order to kind of dissuade those fears a little bit, I've run two benchmarks actually. Here, let's look at raw read performance. So here is the CSV file. It's a fairly large data set. It's about 1 GB. And here we have several systems. We have Postgres, Pandas, Polars, and DuckDB reading this file into a table. This is not an apples to apples comparison, because Postgres and DuckDB actually, write the contents of this file back to the disk, in a transactionally safe way. Binary compressed type saves with statistics and schema, everything. We flushed all the caches. But you can see that while Postgres indeed is slow, it's not an analytical system. It's not surprising. And Pandas and Polars are doing pretty well. But DuckDB, even though it has to do all these extra things to be transactionally safe, to allow you to change your data with confidence later on, it is also still the fastest. So that's a nice thing. Here's another example of changing stuff. So here we have another benchmark where we create a table. It's a synthetic example. The table has 100 columns. They're all randomly, these are just series of data. It doesn't really matter for this example, but we are simulating something that's actually quite a typical change in analytical cases, where we're basically changing in these updates down there, we're changing a single row, and we're changing the percentage of rows that this change affects. So the first update affects 1%, the second update affects 10%, and the third affects 100%. And if we look at the results here, again, we are used for transactional systems being slow, but DuckDB has the world's first analytics-optimized multi-version concurrency control. And so if you look at this result, you see that DuckDB is basically unimpressed by this change at all. And other systems like Postgres or Tableau, for example, will use 70 seconds for this change. It's quite a lot. If you want to read more about this, here I want to point you to 2 recent blog posts that me and Mark, the co-creator of DuckDB, have written. The first one is called Changing Data with Confidence and ACID, and the other one is called Analytics Optimized Concurrent Transactions. If you want to sort of hear more about the examples that I've just shown with the performance. And that's kind of it that I had, or whatever I had. So I was talking about changing data with confidence and acid using DuckDB. In my opinion, transactions are a really great idea for analytics. And yeah, and because of that, DuckDB has implemented world-class transactional sort of handling to support analysts in their tasks. That was it. Thank you very much. Happy to take questions.
Brilliant. Thank you, Hannes. I will show a question on stage now. Very interesting talk. Any architectural advice on how to use DuckDB for an on-cloud AML workflow, which naively has data lake persistence, such as Azure containers or AWS S3 buckets?
Well, thanks for reading the question. It gave me some seconds to parse all the words in this sentence. Yes, I do have some advice. So if you have data lake persistence on buckets, what I've seen people doing is two things. One is you want to run the first general advice is you want to run the DuckDB instance close to this bucket, right? In the same cloud, in the same availability zone, things like that. I've seen two things. People run VMs and then have DuckDB directly talk to the buckets in that VM. And that works really great for sort of interactive use. What I've also seen is people using things like lambdas, which is, I think, kind of cool, to basically run queries. Because DuckDB is so lightweight, you can pull it instance up within a couple of milliseconds, and you can do that in a lambda. And then your lambda can do the data transformation for you and write it back to object store. So that's, I think, and maybe I have a third advice, which is if you're running really like heavy queries, it really pays in an on-cloud environment to have local SSDs connected to your VMs and then putting your database files on that, because that just eliminates a bunch of network round trips. But yeah, it's a use case that's pretty common, I would say. I hope that answered your question.
Cool. Thank you. We have another question. Do you have any use case or stories where DuckDB was used for integration tests to speed up the total time of the run?
Yeah, this is a super common use case actually that we see. So we see lots of people running DuckDB to kind of work out their DBT workflows or work out their analysis steps, also to run like basically the unit tests for their transformations locally, because DuckDB runs anywhere. You can run it on your local laptop. You don't need like special hardware to run it. And we have seen that quite a lot, that people use DuckDB for local testing. What they then usually realize after doing that actually DuckDB is usually good enough to also run on the full data set, and then very often that actually translates into a production use case afterwards. But to answer this specific question, yes, we see that use case quite a lot.
I'm actually curious, just to follow up on this, is there any things to watch out for if, for example, originally we're using MySQL and then now we're using DuckDB for testing, is there any, like schema differences, anything like that?
Yeah, due to the unique way SQL is standardized, there are differences in SQL syntaxes. So DuckDB mostly follows the Postgres syntax because it's such a widespread sort of dialect. We have extended it a little bit to make it with quality of life features. So we have some blog posts, if you're interested, friendlier SQL with DuckDB, I think you can find them. But that's a gotcha. When you're comparing, like running with different SQL dialects, that's sometimes a bit annoying. There are systems that are trying to abstract this. One I like is IBIS, for example, in Python land, that uses SQL Alchemy under the hood to basically construct SQL queries in a system independent way, and we have support for that in DuckDB, so you can use that. There's also other toolkits that allow you to do that, but it's like the differences between MySQL dialect and Postgres dialect are pretty strong, I would say. So you would have to watch out for that kind of thing. Yeah, we actually have a project right now to extend DuckDB's parser with more dialect support. So maybe that's something I would maybe check again. If you need MySQL dialect, maybe check again end of next year or something. We should have that.
Okay, brilliant. I think that's about time for questions. Thank you, everyone. again for joining the session. And thank you again, Hannes, for giving us a very informational talk. Just a little bit of housekeeping notes. If anybody wants to continue the discussion, please do join the Discord channel for PyData Global, and the talk will be available on AirMeet right after this broadcast, and also later on it will also be available on YouTube.
Thank you. Thank you.